Okay, this is hypothesis testing. It's going to try to also bring together most of the things we've learned so far, but in a slightly different way, right? So even if last chapter was not clear, you are able to understand this chapter because it's kind of bringing new concepts, that is complete by itself. Okay. So what we do in hypothesis testing is to make confirmations or verifications of claims, right? So a hypothesis is just a claim, right? A statement about a population property. Okay, so normally you don't make claims about samples. So if I say, for example, the average height in the class is maybe 5.3, it's, or let's say 5.1, it won't be such a big challenge for anybody to verify that, right? I just need time to measure everybody's height, sum it together, divide it by how many persons are in the class, and I have that. But if I say the average height of everybody in the country is 5.5, I think, for females, and I'm not mistaken, then it becomes a big challenge for people to verify that because nobody can actually survey everybody and get everybody's height. So you're not able to verify such claim totally. The best you could do is to use estimation method to try to say, okay, hey, this is way off than what it should be, that I am not trusting it, right? Or this is in the ballpark of what it should be, so I'm trusting it. So for example, if somebody says the average height in the country is 2.2, you are going to say, no, that is like way off, right? That it shouldn't be correct. Okay, so we're just going to be doing the same thing, but now we are using statistical method, and now we are bringing in confidence level. So what we are going to be doing here is to test those hypotheses. So a hypothesis test is just a way of verifying that that claim is too off from the mark to be true, but sometimes the answers will not be as obvious as when I say the height of 2.2 in the nation. So if I say, of course, everybody knows that that is too low, right? Or maybe I said the average height is 7 point something, everybody knows that is too high, right? But if I say it's 5.2 or 5.3 or 5.4, you will be in doubt as to where to fall into, right? And it will be difficult to disprove. So what we're trying to do is to develop mathematical procedure to say, okay, this is too far from what it should have been if it is true. Right? So that is the hypothesis test. Okay. And you could do that by taking a position, right? And then trying to prove against that position. So the null is the position we normally assume. We say it's okay, right? So if somebody is claiming the average height is 5.3, the null hypothesis accepts that to be true. The alternative is what tries to disprove it. Okay. So the formula is being developed in a way that when you're solving through, hoping to disprove the null, which accepts the claim, right? To get the alternative. That is what you're hoping to. So when you're framing research questions are framed that way. So you frame your research question in terms of the null, but you're hoping to be able to find data enough to support the alternative. And let's be developing this a little more. So when we disagree with the null, which is saying the statement, the claim is true, we frame it as that we reject it, right? Okay, so but if you fail to disprove the null, then you fail to reject the null. So this is the language used. But I know in the textbook it's going to say something like accept the null. That is not really proper, right? Accept the null would be like, somebody says the average height in the country is 5.4, and you say, yes, that is true. You don't really know if it is true. Nobody knows if it is true, because nobody has been able to measure everybody's height if it's true. But we can fail to say, we can say, I am not saying it's false. That is a way of accepting it. Okay, so where this applies also is in the law court, right? So after a prosecution, the judge will normally say, not guilty, right? Or guilty. But he wouldn't say you are innocent. No judge ever says that, because nobody knows who is innocent. Case proven today might be found to be false, the next time. So the framing of the law is of a judicial decision is guilty or not guilty. Not guilty, because the opposite of not guilty should be innocent, but nobody says innocent. So it's the same thing, like similar concept here. But from time to time, you're going to see where they say accept the law. But just be aware that that is not the correct phrasing. What we do is fail to reject the law, not accept it. Okay. All right, so by now you would have seen some couple of notation, right? Some symbols here. So if I go back a slide, you see that the null hypothesis is represented with HO or H naught, right? As a null hypothesis. And the alternative is represented by H1, right? Or HA. That is the alternative. That is the way it is denoted. Okay. So a key difference between these two is that the null only assumes one mathematical symbol of equality. All right, let me see what is next here. Okay, so what the null does is to kind of support the claim, right? So the null will always have this symbol here, right? So if, for example, I am trying to compare the example I've been using this morning, maybe average height of everybody, I would say the mu, the population average height, is equal to 5. Okay, so the point I'm trying to make here is that because the null accepts the claim, right, it's always stated as a equality sign. Then the alternative is what kind of counters that claim, right? So the alternative is stated in 3 different ways. So if I say the average height across the country is 5 feet, then there are 3 possible responses you could have, right? One is that, if you're not agreeing with that, there are 3 possible ways you could disagree. One is that that average height is actually less than 5 feet, okay? The other is that the average height is actually greater than 5 feet. Or you could be in the middle, saying, okay, well, I don't know if it is greater, I don't know if it is smaller, but I know it is not equal to 5 feet. These are the 3 possible alternatives. There's no other thing position you could take if you are acting against the null, right? So, and I deliberately use HA here. So you use HA or H1 for the alternative hypothesis. I use H naught for the null hypothesis. Okay, so these are the 3 different ways of writing the alternative hypothesis. Okay, but this is the only one way of writing the null. Okay, and this is the accepted standard. But again, if you're watching maybe YouTube videos or reading other textbooks, you're going to see different things. But this is generally the accepted standard. Okay. Everybody agrees on the alternative, but there are some little different kind of representation for the null. But I've chosen to use this one as the one that most statisticians go with. Okay. Any questions so far? Okay, so the first thing we've been able to do is to recognize the null and the alternative hypothesis, right? And we know that the null hypothesis uses the symbol equality, and it may not be just one sample case, and we're going to see that as we move ahead in this topic. It could be that I am interested in comparing 2 samples, right? So in this scenario, I am comparing the population value with a fixed number. I could also have a different scenario where I'm comparing two different subpopulations. So maybe I say this class and another class, I'm comparing the height of students in both classes. I will have the null stated like this. mu1 is equal to mu2, right? This is saying the other group is equivalent to the other group. Okay. But the key thing here again, you notice is that the null will always use the equality sign. The null just agrees with the claim. The alternative for this one will be this way. If I am disputing the stated null above, I would dispute that there are three possible ways I could dispute that, right? One way is to say, okay, class group 1 is actually less than class group 2, right? Another way to say that is to say that class group 1 is actually bigger than group 2. Okay, I hope you can see that clearly. Okay, I think it came up. So, and then another way to say that is to say, okay, well, I don't know which group is bigger, but I don't think they are equal, right? Again, these are the three different versions of the alternative hypothesis. So again, you notice that the alternative hypothesis is always written with equality sign, right? Why the null hypothesis is always written with equality sign, why the alternative could be written with any of those three inequality expression. Okay. So I hope that is clear now. Any question on that one? Okay, so that's the foundational statement for this topic. So once the hypothesis has been stated, we can now go ahead to prove or disprove, right? So, and we now go ahead to know what to do to either agree with this or disagree with that, right? And if you disagree with the null hypothesis, automatically it means you're agreeing with the alternative hypothesis, right? Because there are two sides to the coin, just like a binomial distribution. So if you flip the coin, if you don't get a head, you tell me you don't have a head, automatically means what you have is a tail. Okay. All right, so let's get to the next slide. So these three situations, to be able to establish these truths, provide evidence to support what we think is the truth, we have to have a basis for doing that. And we go back to our normal distribution. Okay? That's why the normal distribution is central to whatever we're doing in the class, right? So what you just do is to, the Z formula that we've been using, right? Use the Z formula to convert that data set that you have regarding the claim. Use the Z formula to convert it to a Z. So this will be the data set. Then subtract the mean divided by the standard deviation. You get a Z value. And when you plot that Z value, you are likely getting this bear shape. So once you move the data from the raw form, it could be height, it could be pulse rate, it could be blood pressure, it could be anything. Once you move it from, and of course, you use computer to do this very quickly, so you don't go ahead if you have 1,000 data from patient or from anybody, any set of people you're working with, you don't go ahead converting each of them to Z-score manually, right? So computer quickly does that for you. So once you move them to a normal distribution by this formula, then you have a shape like this. And now you can use the theory that have been well established to respond to the claim. I think we can hide this, right? Yeah, okay. So now you can use the theory of normal distribution that we've established before now to solve the problem. So what do? What we do is that if, for example, I'm trying to verify a claim, continuing with the previous illustration, assuming somebody is claiming the average height, so let's put a mean here, is 5 feet, and you think is greater than that. Okay, so let me use a number that will be very obvious. All right, so assuming somebody is claiming that the average height across the country is 3 feet. Okay, you might lean to the direction that is bigger than that. That is more plausible than is less than that. So what you are trying to do is to say, okay, let me collect a sample data, right? Because you prove the claim with a sample. Let me collect a sample data. And then from this sample, find the average in that sample, right? Then use this Z value here, formula here, to convert each of the data in the sample to a Z distribution, and then compute the Z equivalent of 3. Okay, remember 3 is in feet, right? But by the time you use this Z function to convert it to Z, then you have a Z equivalent of 3 feet. Then place that Z equivalent on this continuum. So here is 0, right? Because this is standard normal distribution, this is -1, -2, -3. And as we already know, the negative value doesn't mean anything negative. It simply means that the heights that are in this region are lower than the average in the population, right? So you have +1, +2, +3. So what we try to do is to say, okay, is the height I got when I converted this, is it too far away from the average? Because this is where the middle of the population lies, right? Then the question will be, how far away will it be before I will say it's not true? So we've had this, right? If it goes beyond this green point, think green, and enters into the red area. So if this is our 3 point, and that could be very far, let's say this is our 2.5 point Z value, right? So if your Z value that you got from converting that number goes beyond 2.5, then you're going to say, I don't believe that value is correct. I don't believe the average height is 3. I think it's wrong because it is too far away from what it would have been. It is coming from a normal population, a normal distribution. Okay. So that is how these claims are made. But the question then is, what is in this point? What is the cutoff here? What is the value that you're using to make that judgment? By now you may guess that that value will depend on the confidence interval you want to adopt. So the bigger confidence interval you need, the more you shift to the tail, the stronger the evidence to prove otherwise, right? Okay, so, but I could make this claim to the right tail. Okay, so I'm focusing on rejecting. I see the way the alternative hypothesis is written. It's greater than. So it's telling me that the claim I am making is about the right tail. I don't think it's less than 3 feet, so I'm not concerned about getting an average height less than 3 feet. I feel it's more than that, so I'm trying to test on the right tail. Okay, so this area that is outstanding, where we have this red mark, is the critical value, right? And that area is alpha. And you remember how we use the alpha to get the critical value. So the number here that we need to form our decision is the critical value, right? Anybody recall how we use the alpha to get the critical value? I mean, it's a couple of steps down, but
because isn't alpha it's like the remainder of what you have. So it's like, let's say it was like 99%, you would do 1 minus 0.99, and that would give you 0.01. And then you would divide that by 2. That would be 8 divided by 2.
Right. So this would be 0.01. Okay, yeah. And then you divide that by 2 to get one of the tails, right? Okay, so we're going to be, and you're very correct. That is true. So once you get your alpha, and I'm going to add something to that statement, but once you get your alpha, right, then how do you proceed from moving from your alpha to getting the critical value?
You
okay, go ahead.
You don't know the mean. Do you use T? Oh, no, you don't even know the Z table.
Okay, so that would be a good question to ask. So you want to know if you are dealing with a Z table or a T table. Let's assume we're dealing with a Z table.
Yeah, then you would look. you wouldn't look for like the numbers at the top and the left.
Mhm.
You would try to find 0.01 on the numbers on the chart.
In between, within the chart, within the normal table. That's very correct, right? So that's what we do. So you see that all you need to know to actually get the critical value for which you make your decision is just to know the confidence level. And the confidence level is not any value. The confidence level is the confidence level you chose to attach to that proof. Okay, so if we use the case of the judicial system again, if there is just a civil infraction, the burden of proof is very minimal, right? I just need to establish that this happened to some extent. But if you're dealing with criminal trials, maybe the consequence is, if it is where capital punishment obtains, maybe let's assume that extreme scenario, maybe the consequence is capital punishment. The bar will be so high, right, that you need to prove beyond reasonable doubt that the person committed a crime for the person to be adjudged guilty of the offense, right? So the bar being high or being low is the confidence level. So the researcher is the one who decides what the confidence level will be, okay? So, but generally in the research community, 95 had been taken to be okay, 95%, right? But you could raise that bar. So if they are doing medical, clinical trials on drug, they usually raise the bar, right? Because you are going to be telling somebody that this works to cure this ailment, and you don't want to make that claim if it doesn't, right? You want to be reasonably sure. So it could be 99% confidence level, right? But if people are making prediction about sales, you could bring it down to 95%. I mean, it's just money that will be lost and not human life. Okay, so once the confidence level is established, you can use that to determine your alpha from what we are just told. So, and if I should formalize your answer, thank you, we could say that assuming the confidence level we need for this evidence, I think red will be better. If the confidence level we chose to apply to prove this claim is, let's go with traditional 95% confidence level, then our alpha, okay, we're going to be introducing alpha with actual definition today. Our alpha will be 100 minus that confidence level. So our alpha will be 5%. Okay, and as pointed out, once you get your alpha as 1%, once you get your alpha, it's better to have it in decimal because we are using a table that has the values in decimal. Okay, so once you do this, this is where I want to introduce a little change. So this is where a little change is coming from what we did before in the last class. So please pay attention to this, right? So in calculation of confidence interval, we always divide alpha by 2 because we are trying to pick up the confidence interval in the middle. And so we always have something remaining on both tails, right? If you are trying to project confidence, you don't want to do that on the tail. So I'm trying to pick out confidence interval. So this is a distribution of data, and then take this to be a population, right? So if, for example, I take your exam scores and I plot it, I should get something like this, right? If the assessment is balanced. Some people might score very high, some people might score very low, but majority of people will be in the middle. If you take the height of everybody and plot it, you're going to get something like this. Majority of people will be in the middle. So confidence interval is normally taken out from the middle section, right? So you will always have 2 tails where the error falls, right? It is slightly different in hypothesis testing. In hypothesis testing, you might have a scenario where you know it is not the lower tail. For example, somebody saying maybe the median income is $2,000 across the country. You know, by no means it's not going to be less than $2,000. So you're not going to be concerned with testing whether it is less than. Your focus will be if it is more than, right? In that scenario, you are testing only one tail, and that's we have here right now. We're testing just the right tail. So when I subtract alpha, my confidence level from alpha from 100%, the alpha I got is the alpha I will actually use in solving the problem. I'm not going to divide it by 2. Because my claim is trying to test only right tail on the upper side. I know somehow that it cannot be less than. Okay? All right. I hope you are following with this explanation. So if you have this concept understanding, once you begin to solve the question, because these are where the logic goes wrong, like I said, the answer you solve and the answer will be wrong if you miss the concepts, the logic of the concept, right? So how do you know if you're testing right tail or left tail? It will be in the question. It will be embedded in the question. So when I'm reading the question and I'm trying to solve a hypothesis claim, I'm trying to solve a claim, a hypothesis question, I should be asking myself, is the claim on the right tail or is it on the left tail? Right? So you want to know that to know how you're going to deal with your alpha. But that would determine the alpha you use. So let's, as on this screen, we're on the right tail, we're going to be using alpha of 0.05. So we're not dividing it by 2 to solve this problem. Okay. Let's quickly see the other 2 scenarios. So once I know my alpha, of course, as we explained, you go ahead and find your critical value. So this time I'm finding the critical value as Z alpha, not Z alpha over 2 anymore, because I am testing only the right tail. I have confidence that it's not less than. My doubts, my questioning of the claim is that it is more than. So I'm testing only Z alpha, the upper tail. Okay. So the Z value I get here, because I'm testing the right tail, will be positive. So that is another way to check yourself, right? So if you're testing the right tail, the Z value will always be positive. It can be negative because if you look at the normal table, on the right-hand side, every value of Z is positive. Okay. So there could be the opposite scenario when we are testing the left tail, right? So let's say somebody projects that the median income is $100,000. Okay. If somebody says that, you are going to know that you are going to question it, doubt it, right? And when you're doubting it, you're not going to be doubting it and thinking it's bigger than that. No, like you're almost sure that it's going to be less than that. So when you're testing in this situation, you're testing your claim on the left. So you reverse the test, right, on the left tail. So the diagram as before. So as before, we're also going to get our alpha. As before, that alpha will not be divided by 2 because I'm just trying to test whether it is less than. I know it's not going to be more than, right? So again, you calculate your Z value. But the Z value this time will be negative, right? Because you are on the left tail. You are not concerned with whatever is going on the right tail. The right tail is talking about the value that is bigger. The median is just in the middle here. You are concerned, your claim is that it is less than 100,000. So you're trying to figure out if it is actually less than 100,000. How do you do that? You do that by taking sample from the population and going through the process we described earlier. Okay. So, but that is a second scenario. So your Z value here will be negative. Okay. And again, a negative Z value doesn't mean a negative dollar amount, right? A negative Z value simply means you have a dollar amount less than the claim, or less than the mean. The last scenario is where you are not sure. Okay. If somebody says the average height in this class is 5 points. Okay, let me not use this class because that might be a little biased. Let's say the average height across the country is 5.4 feet. I mean, that doesn't look very bad. It could be the truth, right? But we don't know. I mean, if somebody says it's 7 feet, I will know it's definitely less than that. If somebody says it's 2 feet, I will know it's definitely more than that. But if somebody says 5.4 feet, I wouldn't be very sure where the claim will go. But to verify whether this claim is true, you are going to be checking on both tails because you're not sure where it is going to. So in this scenario, you are going to do two tail. So this will match what we're doing in confidence interval. You're going to divide alpha by 2. So that the z you're looking for this time will be z alpha over 2. Is this making sense? So that way, the claim is checking both sides. It's checking whether it is bigger and whether it is less. The alternative is just trying to say, I know it's not equal to, it may not be equal to 5.4, but I want to check whether it is less than that or more than that. Then you collect a sample data. From the sample data, you do the analysis we'll be doing in a moment. Right? Okay, so there are 3 hypothesis testing you are supposed to, we do ordinarily. And you can see that all of them is coming from the alternative. All of them is coming from the alternative hypothesis. All the tests. So it's either you're doing left tail, or you're doing right tail, or you're doing two tail, right? And then know that your left tail and right tail test, you don't divide your alpha by 2. But for two tail test, then you do divide your alpha by 2. So when you're reading a question in this section, unlike confidence interval where it will always be divided by 2, you want to verify whether you're doing 1 or 2 tail. And if it is 1 tail, you want to know if it is right or left. If it is right or left, you still have 1 alpha. You don't divide alpha by 2. But until you get to a situation where the question is neutral, and then it's trying to test for 2 tail, and then you divide alpha by 2 to get your critical value. Once you get your critical value, all you need to do is to compare the critical value you have with the value you have from the data. If your result is in this section of this red region, then you're going to say, hey, this is too far from the middle, so I'm willing to say that you are wrong. And the claim is wrong. But if you do your z value and you find out that the z value is somewhere here in the green region, the z value is somewhere here, maybe on the left or on the right, you're going to look at this and say, well, it's possible you are right, but I don't know if you're right or wrong. So I'm not going to say you are right. I'm going to say it's possible that you're right. And how do we frame it here? We say we fail to reject. Again, in the textbook, you might see, I think they have a different way of saying this, but this is the standard statement, okay? We fail to reject the null hypothesis. So I'm saying the claim, I don't know. Well, I am not saying the average height is 5 feet, but I'm saying it's not, if it may not be different from 5 feet. All right, so that is what difference is, right? Okay, so these are the 3 tests we conduct. Any question? Okay, so I hope you are picking up this concept slowly, right? This understanding is needed, you know. So unlike chapter 2 and 3, we normally have one thing to solve the mean, solve the confidence, solve the standard deviation, you know. What is the percentile? Just one question, right? But here, if somebody says, test the hypothesis claim, the person is asking you a whole lot of things. Just like if somebody says, calculate the confidence interval, I'm asking you to do all of this, right? So it's important you understand how to do the mean, how to do standard deviation, how to do the critical value, how to do the margin of error before you are able to solve confidence interval correctly, right? Yeah, so, but if you focus your learning on how do I do this, it might become a challenging thing. So I want you to do the same thing on this topic. Pick up everything we are talking about. How do you determine the type of the value of your alpha? You check whether it is 1 tail or 2 tail. You know, is my z critical value going to be positive or negative? If it is right tail, it's going to be positive. If it is left tail, it's going to be negative, right? And then you proceed from there. Okay. So now we've given the general picture. Let's start narrowing down, you know, to a little more details. And today we're going to spend just this class in concept. We're developing concept. By next class, when we come back from the break, we'll start to actually solve problems. Okay, but we might be able to solve some today. So So we've been talking about alpha all this while, right? And we've already known, of course, that the notation is that alpha is given as the difference between all of the normal distribution, the whole, which is 100%, minus the confidence level that you are willing to accept. We know that already, right? But what precisely is alpha here is a definition of what alpha really stands for, right? It is known as the type 1 error, right? That is what alpha is, okay? And in word, it is the probability of wrongly rejecting the null hypothesis when actually it is true, right? It's saying that a claim is false when the claim is true. So like in the previous scenario, somebody claiming that the average height is not 5.4 when actually it is 5.4. You've made an error, and that type of error is called type 1 error. And that type 1 error is what we denote as alpha when we are solving these problems. Okay. Any question on that? So if there is a type of error I can commit by saying that a claim is false when the claim is true, it kind of inversely implies there's also another type of error you can commit if the claim is false and you fail to say it is false, right? And there are two sides of the same thing. So the average height is 5.4. Let's say that is the truth. Then in verifying the claim, you say, no, it's not the truth. You've made an error, right? In judgment or in your decision. So that is type 1 error. But somebody comes around and claims the average height is 2 feet, and you fail to reject that. You just say, yes, it's 2 feet. You accept that it's 2 feet. You've also made an error, right? Because it's actually different from 2 feet. That other error that would be the last one I illustrated here is the type 2 error. So let's look at them more critically. Oh, okay. I think I have some other things, but we'll get to that. Type 1 and type 2 error. But here it's like I should rearrange that slide. And we're just trying to emphasize here that if the null hypothesis is rejected, it means we have evidence to support the alternative, right? So if I have my H naught, and whatever claim H naught is making, I am rejecting that. And you remember how we reject? We reject if we check for the Z value and we find out that the Z value falls on the tail, assuming I'm doing 2 tail. If the Z value falls on the tail, then I'm going to say it's not true because I expect the truth to be somewhere in the middle. So when I reject, it means I am supporting the alternative. Okay, so that's just what this is trying to kind of emphasizing that we've already said that in different ways. Okay, and similarly, when you fail to reject, right, when the null hypothesis is not rejected, it invariably means you don't have enough evidence to support that the alternative is true. All right, so these are two sides of the same coin. So in hypothesis testing, you are going to arrive at a conclusion and you're going to state your final conclusion. So this is just about how that conclusion is stated. You're going to say, okay, I reject the claim. It means I'm supporting the alternative, whatever the alternative is. And you know, the alternative could be 3 possible things, right? The alternative could be that the answer is bigger than the claim, that is right there. The alternative could be that the answer is less than the claim, right? That is bigger. It could be that it's less. It could be that it is not equal to whatever is the claim, right? So whenever you reject the null, you are saying there is enough evidence in the data to align your decision with one of these, right? That's what the first part is saying. And the second part is saying if you fail to reject the null, fail to reject the null, it means you don't have enough evidence to support any of the alternative. That is why you're failing to reject it. Okay. So these are two ways to make conflicting statements. We're going to be taking examples, practicing on this. So let's get back to the idea of type 1 and type 2 error. Okay. It will be a little bit confusing, but with practice, you get comfortable with it. And I have some conceptual questions on that person work that will help you practice on that, right? So whenever you reject the null hypothesis, when in fact it is true, you are making a type 1 error. And whenever you reject the null you fail to reject the null hypothesis, when it is false, you're making a type 2 error. Okay. So I will give you time to ponder on that. And I think I have a page on the website that captures this in a better way, or gives you more room to think about it in the context of our experiment. Okay. So I'll give you a moment to look at this, and then we discuss this further.
Good to see you, and Joe.
Okay. So what is he's trying to use a diagram to illustrate all these scenarios, right? I hope it's making some sense. So just explaining a little more. This section, this direction is that okay, I think red will be better. Okay, blue. This direction is focusing on the true nature of things, right? And we don't know, but hypothetically, we're saying if you're going horizontally on this table, you are dealing with the truth. Okay. Excuse me. This direction is focusing with the evidence in the data. So if you're going vertically down the column, you're dealing with evidence you can find in the data. We wish the evidence from the data is always correct. If the evidence from data is always correct, then we don't need to bother about null and alternative hypothesis, right? But the problem is evidence from data are sometimes wrong, right? You know, depending on the way the sample was gotten, right? So we don't have full confidence in the evidence in data, but the challenge also is that we don't always know what is the truth. So that is the uncertainty we are trying to balance off here. How do you balance that uncertainty? You balance that uncertainty by deciding on percentage confidence level that you want to attach to your answer, right? And that is why one could say there is 95% chance that it will rain today. They are saying, I'm not sure it will rain, but I think I am confident enough to tell you that if there is 100 pieces of possibilities of raining, 95 of them will be rain. Only 5 will not be rain. That's what we're saying, right? And nobody ever comes out to say, I have 100% confidence this will happen, because there are variabilities and changes. Okay, so once you make that confidence level, you have exposed yourself to some kind of error, right? So take, for example, people who are doing political polls, they will project winners on a confidence level, and they will give you a margin of error. That margin of error is associated with alpha, right? Just what we're working with. Okay. So once you make a decision as to what your confidence level will be, let's say the typical 95%, it variably means you are accepting that 5% of the time you are going to be wrong, right? You know, so that is what it means. Okay, so the question now is, how do I know when my result is among that 5%, right? So we are mapping it out in probability. So If, for example, somebody collects data about a situation that is actually true, and after analyzing that data, the data provide evidence supporting that that situation is true, then the right thing has happened. That is a correct decision. There's no problem about that. Okay. If a situation is false, let me get this right. If a situation is false, like the reality of what we know is says that situation is false, but again, somebody collects some data and find out evidence that the situation is true, then that person has made an error. That is where type 2 error comes in. Right? In this quadrant here, I'll come over here. If a situation is truly false, right? And somebody collects data and say that situation is true, that person has also made an error. That is a type 1 error. And finally, on the last quadrant here, if a situation is truly false and someone collects data and claims that situation is false, then that is the correct decision. So you either align with the truth, that is the forward diagonal, that situation will be correct, but whenever you fall to the other diagonal, you are making an error. So depending on where you fall, you could have type 1 or type 2 error. Okay, so let's put this in more concrete terms. So let's look at this definition and we'll look at some questions to make us think through it more concretely. So again, the definition here says, whenever you reject the null hypothesis, okay, the null is the claim that the situation is the situation is this way. Whenever you reject that null hypothesis, it means you're saying it's not true. For you to reject it, it means you're saying it's not true. And whenever you do that, if in reality it is true, the null hypothesis is true, then you've made type 1 error. Okay. The second scenario is whenever you fail to reject the null hypothesis. So if the null hypothesis is false, you should reject it in support of the alternative. So whenever you fail to reject the null hypothesis, when actually the null hypothesis is false, you made a type 2 error. Okay. I'll go through that once more, then we'll look at the charts, the practical exercises. If a situation is true and you conduct a test and you say the situation is false, when actually it's true, you made type 1 error. That is one. On the other hand, if a situation is false, the claim is false, then you conduct a test and you fail to reject that claim, because it's false, you ought to reject it. You fail to reject it, it means you're accepting it. You're accepting false, what is false, and you make type 2 error. So they kind of go opposite. Okay, so let's try this in more concrete. Let's look at some of these questions. I'll come to p-value. Let's look for. Okay. I think it's the last few questions. Let's look at this one here. Okay, I'll give you time to read through it. Then tell me what you think. Type 1, type 2, neither or both of them. Of course, we know it can be both, right? You can make these two different types of error at the same time. That would be one of them. Okay, to help with your answer, let's analyze the question just very briefly. So let's try to read through and pick up what it's trying to say, right? So the Bureau of Labor Statistics reported that 91% of Americans have paid leave in their job, right? Okay, so to verify this claim, normally you do a survey, ask workers, do you have a paid leave? People will check yes or no. And after that survey, somebody realized, after surveying 1,000%, the researcher realized only 89% of them actually had paid leave. Okay. Now, at this point, do you think the department or the Bureau of Labor Statistics, are they wrong by their claim? That is 91%, when actually somebody took a sample of 1,000 and found out it's in that one sample, it's 89%. So just leaving the rest of the question, will you think the claim is wrong from what we are doing in the class?
Well, the claim with the labor statistics is wrong because the study showed that it wasn't right.
It's not so. The claim is 91%, studies shows is 89%. So they are wrong. 91 and 81 are not the same, even though it's more, right? They are not the same. Okay. So that is correct. That's one way to look at it. Did anybody think the answer is that they are right? They may not be wrong. Let's not say they are right. Remember, we don't say they are right because we don't really know, right? Nobody knows the actual truth. I mean, even if the labor Bureau of Labor Statistics, they don't go around asking everybody if you have paid leave, right? They go from the data they have, and the data they have is the data that people submitted. There are people who did not submit. It's just like information from IRS, right? Yeah. Okay. So that's one way of looking at it. But somebody else, so let me add up that because of time. But somebody else can also say 1,000 persons. Who are these 1,000 persons? Right? I can go and get another 1,000 persons. I find out that the value is actually more than 91%. Is that person correct? The person may be correct. Is what you are saying correct? What you are saying may be correct. In fact, the problem is that we don't know. We don't know either way.
We don't have enough evidence.
We don't have enough exactly that. We don't, because we are dealing with a sample of 1,000. The only evidence that could tell us whether they are right or wrong is the evidence that involves collecting data from everybody. And we know in reality that will not happen, right? Okay, so that is what hypothesis testing is trying to do. So if you are forced to answer this question one way or the other, where do you place your answer? Your answer cannot be subjective, it can be sentimental, it can be based on feeling, so that is what the judges do in the court. So they are asking the lawyers, what is the evidence that this person did this? You have to provide concrete evidence, right? So in statistics, we try to do that by using the normal distribution to check whether this value, if you plot from a random sample, even though this is a sample, if this place is 91% as they claim, if by distribution, this 89% is low, of course, is in this region, I would say, hey, this is too far from the middle. So I'm going to say it is not 91%. The Bureau of Labor Statistics is wrong, right? Of course, most often they will not be wrong because they employ the best brains and they have the most resources than anybody, so they're able to find the truth or something. Okay, so that is what we're doing here. So, but for this question right now, we don't have enough evidence and we don't know whether it's true or false. Okay, and so because of that, this second part was set up. Okay, so a researcher conducted a research, and we're going to be talking about p-value when next we meet, right? And found out a p-value of 0.027. The p-value will suggest to you the probability that the answer is true or the answer is false, right? That's what the p-value is, but we're going to be defining later on. But to avoid you from making that thought, assuming you don't know what p-value is, what we know is that the null hypothesis was rejected. That's what we know, right? So the null was rejected. I remember what the null is. The null will always support the claim. So the null here is that the proportion of people that have paid leave is equal to 91%. That is enough. Okay. We don't know the alternative that was tested. We don't know whether the alternative that was tested is that proportion is greater than 91%. You know, it could be that. We don't know whether the alternative that was tested is that proportion is less than 91%. It could be that. We don't know whether the alternative hypothesis that was tested is that is not equal to 91%. It could be any one of these. But again, not having that knowledge will not affect your answer here. Then what you know is that this was rejected, right? If this was rejected, the question then is, what type of error would that person have made? Right? Because we don't know whether it's one way or the other. But what we know from the evidence we have right now is that the person may have made some error. And that error will come from the fact that the decision to reject the null is wrong. So if somebody rejected the null, when the decision to reject that null is wrong, then it's an error. If the person rejected the null, when the decision to reject the null is true, then it's not an error. It's not an error. So assuming the person made an error by rejecting the null, what type of error could that be? Type 1 or type 2 in this scenario? How will you suggest? And don't bother about right or wrong answer. Just, I'm trying to engage your mind, because once you understand all this logic, then when we start to solve the question, when you see any question, you're able to pick it apart and get to the root of the answer. Okay, so I will encourage you to rewatch this video again and next class. So at this stage, don't focus on knowing how to plug the numbers and get the result, because you have decision to make about what is even the formula and what you should be plugging in. Right? We still have 1 minute. So what is your answer to this question? Yeah, please mark on the last row, I think. Okay, just to wrap it up, see, if you look at this place, the only way you can make type 1 error is when you reject. The only way you can make type 2 error is when you fail to reject, right? So in this question, this person rejected, and because the person rejected, because the person rejected, what is possible is type 1 error. Type 2 error is not possible because this person rejected. Okay, next class, we're going to pick it up from here and we're going to try to solve actual concrete questions about this. Okay. If you still have concern with the homework, do your best attempt, take a screenshot, send it to me. I can give you specific feedback. Okay. Please mark on the sheet before you.